Okay, I'll go ahead and get things rolling here. Welcome to Coatings Talk live chat, this live audio chat. I appreciate having you participating with this evening's session. Going to be covering basics of corrosion and reinforced concrete. The last episode that I had, our last session, excuse me, about almost 2 weeks ago, covered the causes and repairs of concrete cracks, and a lot of good responses came from that particular session. So I decided to go into concrete again and kind of cover some of the basics of corrosion. But before I go ahead and roll out the conversation and also cover some of the topic, what I'd like to do is cover disclaimer. So first off, I want to say greatly appreciate everyone joining this evening. As we're getting started, I'd like to cover the chat session disclaimer. This live chat and the Coatings Talk series does not represent the opinions or strategies of AkzoNobel International. And additionally, I make every effort to provide accurate and up-to-date information from not only the global protective coatings industry, but other related industries as well. Despite this care and attention, it's reasonably possible that content and chat conversations within this live broadcast may have content that is incomplete and or incorrect. The other thing related to this broadcast, I am recording the session for rebroadcasting and also to have an archive recording. So this live chat, use of the recording, distributing of any of this content is not permitted out without written permission of me, Jim Kunkel. So appreciate that. Now, before we go ahead and get into the conversation, I'd like to let you guys know how you can participate with the live chat. All you really need to do, it's on your bottom bar, the menu bar down there. You can react. You can also raise your hand. If you raise your hand, that's when I will bring you up to the stage, open up your microphone, and you'll be able to participate, ask questions. But in addition to that, as Rudy just did, you can also hit reactions, give me a thumbs up, a clap, a heart. I always appreciate the hearts. But that's a good way to participate as well, just so that I know what I'm covering is valuable and you guys are getting some enjoyment out of it. So looking forward to having this conversation. Let me bring up Jim. Jim, I'm going to bring you up here. And you were there. You can unmute yourself, Jim, and please feel free to comment before we get started.
Well, can you hear me?
Yes.
It's great. Glad to be here, and it's a great evening, and looking forward to hearing what you guys got to talk about coatings and corrosion. I've done
Perfect.
for over 35, 40 years in corrosion and tank coatings, vessel coatings, and look forward to sharing.
Appreciate that. Jim, I'm going to go ahead. I'm going to send you back in the audience, okay? There we go. Okay. So I don't know if you guys know this or not, but did you know that concrete is the second most used man-made material? The other thing about with concrete, it is a very complex material, and from the aspect, at least on my side, on the coating side, and sometimes when it comes to preparation, a lot of times that concrete is poorly understood. It tends not to be something. It's sometimes it can be a wild west. I always look at when it comes to steel prep and use of coatings on steel. They tend to be a certain way, but concrete, it seems still to be a wild west. But the one thing about concrete that really kind of adds in an opportunity for corrosion is the way that we use it for building, construction, and infrastructure. Steel reinforcement is added into concrete, and it's really to improve the concrete's tensile strength. Now, not typically, but at the beginning life cycle of concrete, it has a high pH level. And then the other thing too with the rebar, you have that pH that's high, but you also have depth of cover where you'll have it embedded in and it's covered top and bottom, and that rebar, that steel reinforcement rebar, is helping to maintain that tensile strength. But over time, due to cracking, you're going to have water that will penetrate. You have to really think of concrete as like think of capillary, think of like a living, breathing type of thing where water will flow, moisture will flow. There's all types of factors that go in, but over time, what typically will happen is as you have ions getting in there, you're talking about some of the uh, chemicals that might be, that pH is going to start to lower from carbonation. There also could be electrical potential changes within the steel, and that's going to bring on corrosion. Now, rebar, steel reinforcement, and rebar, excuse me, is made from iron. Steel is made from iron, and what tends to happen is you have iron that's used and a whole lot of energy that's used to create it. And what that steel wants to do, it wants to go back. It's really fighting to go back to its original state. The reinforced concrete, I did not know this, but it was first introduced and patented in 1867 at a Paris exhibition. And this is kind of where a lot of it, as I read in the things, it said, with it being used for reinforcement, you had, from the early days, they realized that corrosion is inevitable. It's going to happen, and now there's ways. Obviously, how do you deal with it? And a lot of things have been done. So you can have, coatings and to help kind of create that barrier. If you have a tank or you have some type of cargo commodity inside, to kind of create that barrier. The other thing that I've seen is that you have sometimes other types of materials that are put in to reinforce the concrete. And the other thing is epoxy coated steel reinforcement or rebar coating, epoxy rebar, excuse me. Typically, a lot of times when you're handling it, you're moving it around, you're working around it, you can have, epoxy coated rebar. It doesn't take much. You have just a small pinhole intrusion, and that can be a point of entry for corrosion to really start. But when I had taken my concrete coatings inspector level 1, my instructor was Bob Murphy. And Bob had, he said, two truths about concrete. The first is that concrete will crack. And the second, he said that the steel rebar is it's going to rust. So as I always looked at it, there's really no escaping the inevitability of those two truths. Eventually, both are going to happen. Now, concrete cracks, again, as I mentioned, it's because it's comparatively weak in tensile strength. And then you also have expansive forces that develop within the concrete. And then in addition to that, because of the reinforcement, the steel is made from iron, it really has that goal of going back into its original state. So it really opens up the opportunity for corrosion to happen. Now, as I mentioned earlier, when you have concrete, you have to think related to the composition of it, that it has to be thought of as a hard, wet sponge. Now, technically, it's a little bit more of a complicated composite material that contains or consists of aggregates, water, and mixtures of hydraulic cement, hydration products that are mostly calcium silicates, calcium aluminates, and other trace materials. The hydration products consist primarily of calcium silicate hydrate, which would be called a gel, and calcium hydroxide, called portlandite. Water is chemically bound in the gel as well as within pores around and between the portlandite and aggregate particles. Now, the pore water is saturated with calcium hydroxide and other soluble minerals such as sodium and potassium salts, and is free to evaporate or move within the concrete. That's that capillary action. Both the size and the quantity of the pore structure depends upon the amount of water added to the cementitious binder system. Within desirable smaller pores, they can form as the mixing water content decreases, provided there is sufficient binder to coat and fill the spaces between the aggregate and the particles. Now, concrete needs water for the cement to hydrate to form these minerals. Now, however, water in excess of that required for properly hydration, it really dilutes the performance properties of the hardened material. Now, admixtures are they would be additives that are put into freshly mixed concrete to modify both the plastic and the hardening of concrete. And these can react with other, with the Portlandite to reduce the porosity of the concrete. Now, water reducers that reduce porosity through improvement of the dispersion of ingredients and corrosion inhibitors that help stabilize the passivating layer between the reinforcing steel and the concrete to extend the time until corrosion begins. Now, in addition to these improvements in the concrete properties, how deeply the reinforcing steel is embedded with the concrete is a significant factor in the amount of time before corrosion begins. This is called cover, and cover is necessary for the steel to create composite action within the concrete and to properly function as designed. Additionally, the cover insulates the steel from exposure to fire and deterioration from materials, the internal materials, and also external environment. Now, two of the most common materials that can be produced are going to be, or that can be detrimental, are carbon dioxide and chloride ions. Now, let's talk a little bit about carbonation. As I mentioned earlier, when cement hydrates, we talked about the CSH gel. We talked about the gel and Portlandite. They're formed. Now, both of the materials are strong alkaline, and still in such an alkaline environment forms an insoluble protective passivating oxide layer that is one of the benefits from combining concrete with steel. Now, the high pH of concrete will fall as the concrete ages, mostly due to the reaction of Portlandite with the carbon dioxide, CO2, in the humid environment of concrete. Now, this process is known as carbonization, and it occurs either as acid rain or by CO2, by carbon dioxide gas diffusing within the concrete and reacting at the surface of the pores to cause the passivating layer, at the still surface in the concrete to dissolve and corrosion to initiate. Carbonation is a slow process depending on the porosity of the concrete, the thickness of the cover, and the concentration of pH reducing materials. Additionally, also too, the amount of moisture in the concrete is a big factor as well. In very wet concrete, the diffusion of acidic materials into the concrete will occur within liquid-filled pores, and it is quite slow compared to the movement of gaseous carbon dioxide through air-filled pores. In water-saturated concrete, the hydrated cement paste will dissolve at a rate depending on the type and concentration of the aggressiveness of the acid that's present and the removal of reactionary products through abrasion or flow of liquid to expose fresh, unreacted concrete to further acid attack. This is the deterioration that happens. In extremely dry concrete, there is insufficient moisture at the surface of the concrete pores for the formation of carbonic acid and the reaction with the Portlandite to form calcium carbonate and water at a measurable rate. The maximum rate of concrete carbonation occurs at an internal relative humidity of about 60%. Wetting a drying of the concrete may accelerate carbonation, but the formation of calcium carbonate might also tend to block some of the very fine pores that will reduce the rate. Now, when we're looking at chlorides over aggressive ions, the presence of chloride or other aggressive ions also will destroy the passivating film on the surface of the steel. However, this process is much more localized than the corrosion from carbonation. Chlorides may be present from the materials used to make the concrete or migrate into the concrete from applied. We're looking at road salts, for example, or airborne chlorides from nearby seawater. Some chloride is captured by by concrete hydration products, and many remain bound until the pH or the temperature reaches some threshold. the chloride ion reacts within the concrete. By remaining present to react further, a pitting type of corrosion can occur. As the pit grows deeper, the acid formed by the splintering of water further accelerates corrosion, causing pits to form deeper and deeper into the reinforcing steel. Sorry, I got my notes here. They're sticking together. There we go. Let's talk about cracks. Most deterioration, damage, or failure of concrete is seen as cracking. Cracks are both the cause of these issues as well as the observable effects. Since concrete is comparatively weak and in tension, expansive forces in the concrete or tensile stress imposed on the concrete will easily exceed its tensile strength. Now, cracks follow the path of greatest weakness through the concrete, beginning at small defects and then propagating as stress increases. New cracks form once the initial crack meets a sufficient resistance and the path of the stress changes, or the ingress of the crack and the material. Causes new stresses to develop. Once a crack forms, it becomes a freeway for materials. Wait 1 second here. Once a crack forms, it becomes a freeway for deterioration by funneling water and dissolved minerals deeper into the concrete. When water freezes in the crack, the expansion forces of ice will force the crack faces to become wider, and when water evaporates from a crack, the dissolved minerals such as chlorides are left behind. So we were talking earlier about road salts, and you also have dust and other type of debris will accumulate within the crack, keeping it open to further infiltration. When the cracks inevitably reach the reinforcement steel, the corrosion begins in a localized area, and then expansive forces from the reinforcement corrosion further widens the cracks as well as creating new cracks. So let's talk a little bit about corrosion principles. Corrosion is an electrochemical process, and what that means is that both chemical reactions and the electrical process occur simultaneously. Usually the electrical process involves ions changing their state by gaining or losing electrons, which is known as oxidation and also reduction reactions. Chemical reactions form new chemical compounds. Now, for corrosion to occur, 4 components must be present: an anode, a cathode, electrical path, and an ionic path. In reinforcing steel, rust forms at the anode where electrons move away and oxidation occurs. An equal reaction must also be present at the cathode where the electrons are attracted and reduction occurs. The electrons formed in the anode travel through an electrical path to the cathode, in this case the reinforcing steel, and external sources such of current, such from a dissimilar metal corrosion or more noble metals in contact with the steel, or stray current leakage can also drive reinforcing steel corrosion reactions. Likewise, ions migrate through an electrolyte, and in this case, the water in the concrete pores. Steel is a very good conductor of electrons. However, concrete may readily conduct ions if it is moist with many pores, or poorly if it has low internal relative humidity and very dense pore structure. Now, the anode and the cathode in a corrosion cell may be adjacent to each other and have different surface areas or be widely separated. Both the anode and cathode are free to move to different locations depending on the conditions of the reaction, and the ratio of the anode area to the area of the cathode is also very important for the rate of corrosion reaction, with small anodes and large cathodes creating a much more intense oxidation of the steel in small areas. Like most other chemical reactions, elevated temperatures accelerate the reaction, and greater concentrations of the reacting materials such as chlorides, moisture, oxygen, also increase the rate of corrosion. Ionic movement essentially ceases during freezing, and corrosion therefore stops. Now, some of the anti-corrosion treatments that can be done, you're looking to do really an interruption or a restriction of the corrosion components, of those four corrosion components. Now, if you do that, it will slow down the rate of corrosion, and this is really the basis for all treatments to really address corrosion and reinforcing steel in concrete. Now, alternative reinforcement, the most effective method to address reinforcing steel corrosion is to substitute for the steel for a reinforcement material that is less prone to corrosion, such as stainless steel, which in most cases is not going to be practical, or other specialty alloy bars, or as I've seen a lot of times, fiber reinforced polymer materials, which are called FRPs. With no material to corrode, the root cause of corrosion is definitely removed. Far too often steel that is used for reinforcement concrete is already significantly corroded. So if you've been to any type of job sites, you might have seen rebar that is already on its way down the path of corrosion. It could have residual mill scale from manufacturing, and then the other aspect of it too, you're going to have some elements typically of light surface rusting, and it might not be detrimental, but really when you start seeing that heavy rusting, that's giving that corrosion a head start. The other thing too that I've seen is with rebar that has epoxy on it. A lot of times, like I say, you just need just a small pinhole sometimes for corrosion to start at that location, and it just spreads within that rebar. Now, electrochemical treatments, external source of electrical power can reverse the corrosion reaction by changing the direction of the electron flow through the steel to reverse the flow of ions from the anode to the cathode. And this is a principle of both galvanic and impressed current cathodic protection. In galvanic cathodic protection, a competing corrosion reaction is used to outpace the oxidation of the steel through the use of a sacrificial anode material, and then it makes the steel the cathode. Galvanic corrosion protection comes in many forms, from discrete galvanic anodes to provide localized protection from changes in the anode and the cathode locations caused by repairs. And let's see what else we could cover here. In all cases, the galvanic material must be in electrical contact with the reinforcing steel, as well as have an electrolyte with the ability to permit the passage of ions between the anode and the cathode steel, or I'm sorry, cathode. With galvanic systems producing their own power and corroding due to many of the same factors influencing the corrosion rate of the reinforcing steel, these systems, although consumable, are relatively maintenance-free throughout their life cycles. An impressed current cathodic protection, which is called an ICCP, an external electrical source of direct current, is applied to the embedded anodes to also force the steel to become cathodic. And the voltage and current of this impressed current may also be optimized to repel chlorides from the steel. ICCP systems must be connected to all metallic objects in the concrete to prevent them from corroding. They must be designed to produce a relative uniform current distribution throughout the concrete structure in changing environmental conditions, or otherwise some areas of the steel may corrode and other areas experience issues from excessive current flow. And ICCP systems must also be robust to remain operational throughout the lifetime of the structure. Really, for these reasons, this type of system must be designed, installed, and maintained and monitored correctly to ensure that corrosion is prevented or controlled, and are somewhat expensive. They can be expensive throughout the life cycle of the concrete. Drying treatments. Most deterioration mechanisms of concrete involve the presence of water, and you have freeze-thaw deterioration, alkali aggregate reaction, sulfate attack, as well as general corrosion. Now, materials may be applied to dry the concrete and increase the resistance to ion flow. Penetrating sealers or breathable coatings come into mind, and then since chlorides move throughout the concrete with liquid water, further ingress of these ions also slows as the concrete dries and further water penetration is inhibited. Barrier materials such as waterproofing membranes and anti-carbonation coatings may be used to stop water or carbon dioxide from penetrating into the concrete, but may also be sensitive to the amount of moisture present in the concrete during application. Non-breathable barrier materials may trap water in the concrete, leading to deterioration from other causes. Sealer coatings or membranes, they are subject to deterioration and really should have routine inspection and also proper maintenance programs to ensure a continued effectiveness. Now, regarding corrosion inhibitors, inhibitors may be added to the concrete either as admixtures when the concrete is placed or surface applied to make the passivating film on the steel surface more resistant to chloride attack, dissipation from carbonation, or otherwise more durable in adverse conditions. The inhibitor concentration required for effectiveness is often dependent on the extent of corrosion conditions for the steel, and for inhibitors to be effective for steel passivization, they must also react with the passivating film on the steel surface. Now, reinforcing steel coatings. Coatings may also be applied to the reinforcing steel to create a barrier between the steel and the concrete. If perfectly, and I'll stress that word, if perfectly applied over the entire steel surface, these materials can be quite effective. However, even a small defect in the coating, again, very small, it could be a pinhole, in the coating can create strongly concentrated corrosion from the small anode to a large cathode area ratio, and that causes a rapid deterioration. The same situations exist with reinforcement coatings applied during repairs, when the reinforcement continues through the repair into the original concrete. Corrosion in this case may be accelerated at the bond line of the repair material to the original concrete, further enhancing the ring anode effect. And then let me cover also close up with oxygen availability. Oxygen availability can also inhibit corrosion, such as in deeply immersed structures or where treatments are applied to the reinforcement surface or to completely encapsulate the concrete. Once the available oxygen is consumed by corrosion, the rate of the reaction will reduce and be controlled by the ingress of oxygen. However, areas immediately adjacent to these inhibited areas may experience accelerated corrosion since the oxygen depleted area are cathodic compared to the exposed sections that become an anode. And with that, come to the end. Does anybody have anything that you would like to add? Feel free to raise your hand and come up on the stage with me. All right. Well, I appreciate everybody this evening. I will take the archive and I will put it out onto my YouTube channel, and also take the audio and put a link to that also on LinkedIn as well. So thank you, everybody. Just one quick update. Monday evening, I will be doing a live stream on my YouTube channel and also on LinkedIn, covering a preview of the AMP annual conference in Denver that's coming up, and I'm going to be talking about some of the key things that I'm looking at related to the technical program, other events there, and it's a good opportunity to, if you want to join me, get in the conversation, and we can talk about the good stuff that looks like it's going to be happening in Denver about a week and a half from now, roughly. So I'll be doing that on Monday evening. All right, everybody, have a good rest of your evening, your day, your morning, wherever you're at. Thank you.